Hey guys, we're back with the final exam review, and in this video we are going to do a couple problems using related rates, and then we are going to do a couple problems involving graphing. Now we might not actually graph the functions, but we're going to go through all of the properties of those kinds of problems, i.e. find increasing, decreasing, asymptotes, concavity, relative extrema, inflection points, things like that. The stuff that you need in order to graph the function. But what we're going to start off with is related rates. So, related rates. What is this? Well, given a certain situation, we're going to use given rates and implicit differentiation to try and solve for different quantities. So, much like the optimization video, I'm going to go ahead and write out the word problem, and then we'll get straight into it. Okay, so suppose that a particle is moving along the parabola y is equal to x squared plus 3. When x is equal to 1, its horizontal velocity is 5 meters per second. We wish to find its vertical velocity at that point. So here's what we're going to do. Let's draw a little picture. The function x squared plus 3 looks a little something like this. And we know at the point x is equal to 1, the function is moving in this direction at 5 meters per second. Its horizontal rate of change is 5 meters per second. What we wish to find is what is its vertical velocity at that point. So we know how fast it's moving left or right, or the change in x. We now wish to find what's its movement, or what's its rate of change going up and down, or what is its change in y. All right? So when you're doing a related rates problem, the best thing to do is write down what is given, what do you wish to solve for. So that's what we're going to do. What have we been given? Well, we've been given that y is equal to x squared plus 3. And we have given that the change in horizontal velocity is 5 meters per second, or the change along the x-axis, or the change with respect to x, is 5 meters per second. Now, what do we have that describes the rate of change? The derivative, or in this case, the derivative of x with respect to time is equal to 5 meters per second. Notice we're not differentiating with respect to x. We are differentiating x with respect to t. When you're doing related rates problems, you're going to be differentiating with respect to time. We're going to be using implicit differentiation. If you don't remember what implicit differentiation is, please go look over the lecture notes from chapter 3. I believe it's section 3.6. All right? So we have what we're given. Now we need to ask, what is the question asking? What's it asking us to solve for? Well, in this case, it's asking for the vertical velocity, or what is the change in y with respect to time. How can we write down the change of y with respect to time? Well, that is just dy dt. That's what we've been asked to solve for. So that's what we're going to solve for. So we know y is equal to x squared plus 3. Now we need to differentiate with respect to time. So we get dy over dt is equal to ddt of x squared plus ddt of 3. Well, that's just going to be 2x dx dt. That's from chain rule and implicit differentiation plus 0. Why 0? Because the derivative of a constant is 0. Just is. It always is. So we have dy dt is equal to 2 times x dx dt. Now, to solve for dy dt, we have required x and dx dt. We have our x value, and we have our dx dt value. So using that information, we can conclude dy dt is equal to 2 times 1 times 5, which is equal to 10 meters per second. And that's how we're going to tackle a problem like this. Once you kind of get the idea of what related rates problems are asking you to do, i.e. come up with an equation that relates all your variables, differentiate with respect to time, plug in what you have, solve for what you don't, related rates are very straightforward. So we were given our function. We didn't have to derive it, but since we're given it, we have our function y is equal to x squared plus 3. We were given dx dt. We want to know dy dt. So we took our equation, differentiated with respect to time, plugged in our values, and we got our result, which is in this case 10 meters per second. And that's how we go about solving this problem. So I'm going to pause it and I'll write down the next related rates problem that we're going to look at. So car A is driving west towards an intersection at 50 miles per hour. Car B is driving north towards the same intersection at 60 miles per hour. How fast are they approaching each other when A is 0.3 miles from the intersection and B is 0.4 miles from the intersection? All right, let's go ahead and sketch this out. Let's say right here, we have our intersection, I. Down here, we have car B. Over here, we have car A. Car A is driving west. I apologize. I built that mirrored. So let's call this the intersection. This is car A, who is driving west towards the intersection at 50 miles per hour. Down here we have car B, who is driving north towards the intersection at 60 miles per hour. The question is asking how fast are A and B approaching each other when this distance x is equal to 0.3 and this distance y is equal to 0.4. So we have a constant speed of A going towards the intersection at 50 miles per hour, B moving towards the intersection at 60 miles per hour. We want to know how fast the distance between them is changing. Let's call this quantity z, just for giggles. And so when x is equal to 0.3 and y is equal to 0.4, we wish to figure out how fast this distance between them is changing, or how fast are they approaching each other. In this situation, we have a triangle. What's the best way to relate variables in a right triangle? You guessed it, the Pythagorean theorem. X squared plus y squared is equal to z squared is the Pythagorean's equation. So we know we want to use that, and we know we need to differentiate this with respect to time. And so if we differentiate this whole thing with respect to time, we get 2 dx, or 2 times x dx over dt is equal to 2y dy dt is equal to 2z dz dt. And since they all have 2's, we can clear out the 2's, and we get x times dx over dt plus y dy dt is equal to z dz dt. Now what we need to do is first figure out which quantity we want to solve for. Well, we are talking about the rate of change between the cars A and B, or the rate of change of the variable z. So this is the one we wish to solve for. But to do that, that means we have to have all these other pieces of information. Do we have x? Yes. Do we have y? Yes. Do we have dx dt? Yes. Do we have dy dt? Also yes. Now, I made a small teeny-weeny error here, not in the numbers, but in the sign of the errors. Notice we are coming towards the intersection. So that means these quantities are negative. Negative 50 miles an hour and negative 60 miles an hour, because their distance to the intersection is getting smaller. It is decreasing. So these vectors, these velocities, need to be negative, because velocity is speed with direction. So Let's not forget the negatives. All right. So we have our dx dt, dy dt, x and y, but we're missing z. How can we get z? The Pythagorean theorem again. We know z squared is equal to 0.3 squared plus 0.4 squared, so that implies z is equal to 0.5. Ain't that handy? Now we can plug everything into this equation. So we get 0.3 times negative 50 plus 0.4 times negative 60 is equal to 0.5 dz dt. Excellent. So from here, now we just need to solve for dz dt. And by doing this calculation, we can conclude that dz dt is equal to, we can conclude dz dt is equal to 78 miles per hour. So that's what dz dt is. We figured out an equation that represents all our variables. We figured out what all our variables are, differentiated with respect to time, plugged it in, and solved for the quantity we wish to have. That's the exact same process for related rates. So to get good at related rates, just practice. Start figuring out that philosophy. Figure out the equation that relates them, differentiate it with respect to time, plug in all the variables that you have, solve for the one you don't. There you go. And that'll get you a related rates problem virtually every single time. All right? So that's all I have for the related rates. Now let's move on to the graphing questions. Consider this function f of x is equal to pi times sine of x on the interval 0 to 2 pi, both inclusive. And part A asks us, where is f increasing and decreasing? Okay. How do we determine where a function is increasing or decreasing? We take the derivative, we set it equal to 0, and then we have our intervals. We test value from each interval, test it at the derivative. The sign of that test value gives us the sign of the function, or the sign of the derivative on the whole interval, which will tell us where f is increasing and where f is decreasing. So, first thing we need, the derivative of f. Well, f prime of x is simply pi times cosine of x. That's it. Is equal to pi cosine of x, because the derivative of sine is just cosine. Now we set that equal to 0, or in other words, where is cosine of x equal to 0? Well, this is where knowing your unit circle is going to come in very handy. So on the interval 0 to 2 pi, there are two values that make cosine of x equal to 0. What are they? Well, x is equal to pi over 2 and 3 pi over 2. So those are the two values that make cosine of x 0 on that interval. So to find the increasing and decreasing, well, we need to build our little chart. Call that 0, 2 pi, pi over 2, 3 pi over 2. Now what we need to do is pull out test values from each of these intervals. So from here, let's pull out pi over 4, and then from here, what do we want to pull out? 3 pi over 4, and then from here, let's pull out, say, 5 pi over 4. Those are going to be our three test values. And so when we test cosine on these values, i.e. we plug these values in, we get that cosine is positive on this interval. We get that it is negative on this interval. And then at 5 pi over 4, what do you know? We're back to positive. So that tells us on this interval right here, we're increasing. On this interval, we're increasing. On this interval, we are decreasing. So that's what we need to do. We can write that down as we are increasing on the interval 0 to pi over 2, open, union, 3 pi over 2 to 2 pi, closed. Be careful with open and closed here. We're including 0 and 2 pi, but we are not including pi over 2 and 3 pi over 2. and then we are decreasing on the rest, or pi over 2 to 3 pi over 2. Now, by the way, if you ever see me make a mistake on one of these things, please let me know. That way I can make sure it gets fixed. All right? All right. So now we have where it's increasing and decreasing. Part B asks us to find the relative extrema, i.e. find the relative minimums and the relative maximums. How can we do that? The first derivative tests. So let's just look at our chart. We have 2 critical points. That's where our relative extrema will occur. Pi over 2 or 3 pi over 2. If you notice, at x is equal to pi over 2, we're increasing, we stop, and we start decreasing. So at x is equal to pi over 2, we have a relative maximum, and at x is equal to 3 pi over 2, since the function is decreasing down to 3 pi over 2, stops and then increases again, at x is equal to 3 pi over 2, we have a relative minimum. That's all there is to that. So if you do your first part of this problem correctly, then the finding relative maximum minimums is just reading that chart correctly. And once you read that correctly, you are good to go. All right? So now let's look at part C. This asks us to find where is f concave up and concave down. Well, how do we find concavity? Well, to find concavity, we need the second derivative. And we know f prime of x is equal to pi cosine of x. So that tells us f double prime of x is equal to negative pi sine of x. And we want to set that equal to 0. So in other words, we want to figure out where sine of x is equal to 0, because that'll give us the points where the second derivative is equal to 0. Since it's continuous, these are the only places where the function might not be concave up or concave down. Remember, that's what we're looking for when we do these problems. Where is it neither? Because we figure out those places, then we can do our little representatives from all our intervals, test those values, and that'll give us for the entire interval what we're looking for. And now we want to know, where is sine of x equal to 0 from 0 to 2 pi? Well, sine of x is equal to 0 at x is equal to 0, pi, and 2 pi. So we have 3 points we need to check, or 3 parts of the interval. So in here we can draw our little chart. But notice, since 0 and 2 pi are at the endpoints, we don't really care what happens outside of the interval. So if we're being realistic, we really only have to check where x is equal to pi. So now we need to pull out test intervals. Here, let's pull out pi over 2, and then let's pull out 3 pi over 2, and then test those values inside our second derivative. Well, sine pi over 2 is 1, so that's positive, so that tells us we're concave up on this interval. And at 3 pi over 2, sine is actually negative 1, which tells us we are concave down on this interval. And now we just need to write this up in interval notation. So we have concavity up from 0 to pi over, so 0 to pi, non-inclusive of pi. And we're concave down on pi to 2 pi, inclusive to 2 pi. So that's how we determine concave up and concave down. Now, for part D, find the inflection points if they exist. Now, how do we find inflection points? Well, the first thing to do is ask ourselves, what is an inflection point? Well, an inflection point is where a function changes concavity and if the function exists at that point. So we have a point of inflection if the function changes concavity at that point, and the function exists at that point. So, what's a quick way to do that? Look at this little chart up here. We see at x is equal to pi, to the right of it, it's concave down. But to the left of it, it's concave up. So that tells us our function changes concavity at x is equal to pi. And also, if you'll notice that x is equal to pi, our original function definitely exists there. So we have a point of inflection at x is equal to pi. So at x is equal to pi, we will have an inflection point, i.e. we will change concavity. Now the last part of this question is to use this information to graph the function, but I'm going to leave that up to you to do on your own. If you want to sketch that out and send it to me for me to check it, I am more than happy to do so, but I'm going to leave the graphing part of this up to you. And what we are going to do is go ahead and move on to another graphing example. So let's consider another function. In this case, f of x equal to 1 divided by x squared. First step we want to do, find the asymptotes. So when we're finding asymptotes, there are vertical and horizontal asymptotes we need to check for. So let's just start with the vertical asymptote. Recall, we have a vertical asymptote at a point if the limit as x approaches c of f of x is equal to plus or minus infinity. That means at that point we have a vertical asymptote. Now finding vertical asymptotes is kind of guessing. You kind of have to look at your function and try and guess where you think a vertical asymptote might occur. Vertical asymptotes will most likely occur when you have a division by 0. And so if we look at our function 1 over x squared, at x is equal to 0, we have a division by 0, hence 0 is not in its domain. So that's probably a good place to check to see if we have a vertical asymptote there. So take the limit as x approaches 0 from the right of 1 over x squared. Well, what's that equal to? So we're punching in values of 0, getting closer and closer and closer to 0 in the denominator. So the denominator is going to get arbitrarily small. And when the denominator gets arbitrarily small, what happens to the whole thing? Well, that means the whole thing is going to blow up towards infinity. So the limit as x approaches 0 from the right of 1 over x squared is equal to infinity. Hence, so we have a vertical asymptote at x is equal to 0. So at x is equal to 0, we have our vertical asymptote. Now how about a horizontal asymptote? Well, to do that, evaluate the limit as x approaches infinity of 1 over x squared. So this is kind of the inverse of the previous part. Now we're punching in arbitrarily large numbers into this fraction. And what happens when you have a fraction and the denominator is getting arbitrarily big? Well, then the whole thing is going to get arbitrarily small. Hence, this limit is equal to 0. So we have a horizontal asymptote at y is equal to 0. So that means on the x-axis, y is equal to 0, we have a horizontal asymptote for this function. And we have at the y-axis, that straight vertical line, we actually have a vertical asymptote. So that's part A, how we find the asymptotes. Vertical asymptote is, take a guess where you think a vertical asymptote might be, check it with the limit. And for the horizontal asymptote, take the limit as x goes to plus or minus infinity and see what it converges to if it does. If it converges, there's your horizontal asymptote. If it doesn't converge, you don't have a horizontal asymptote and you can move on with your life. All right, so that's it for part A. Now part B. Find where f is increasing and decreasing. So I'm finally going to change colors again. So we want to find where f is increasing, decreasing. How do we do that? Take the derivative, set it equal to 0, find our critical points, check our intervals, determine the sign of our test intervals, and then that'll give us increasing and decreasing. But to do this, we first need the derivative. But we know f of x is equal to x to the negative 2. So f prime of x is equal to negative 2x to the negative 3, or negative 2 over x cubed. So notice this function is actually never equal to 0. A fraction can only be equal to 0 if the numerator is equal to 0. And since the numerator can never be 0, this whole thing can never be 0. But that's not the only place critical points can occur. Critical points can also occur at where the derivative does not exist. Where it does not exist. So, where does this not exist? At x is equal to 0. So at x is equal to 0, f prime of x does not exist. So the derivative does not exist at this point. Now, we need to do our little chart, test the intervals to the left and right of this, and that'll tell us where it's increasing and decreasing. All right? So, build our chart. This middle point here, we have x is equal to 0. So the left of it, let's pull a test value, say negative 1 and then 1. And let's test our function at those values. So at negative 1, what is our derivative? It's actually positive. This function is increasing. Now, what about positive 1? Well, it's negative. So we're decreasing on this interval. So what can we conclude from this? We're increasing on the interval negative infinity to 0, non-inclusive on both ends. Why? Negative infinity is not a number, and 0 is an asymptote. We don't have any sign at an asymptote, so we can't include it. And we're decreasing on 0 to infinity. Still, non-including the endpoints for the exact same reasonings. So now we have found where f is increasing and decreasing. Now part C. Find any relative extrema. So we want to find the relative extrema. Well, let's go up here and look. Notice that x equal to 0, the function does change our signs. So x equal to 0 is a really good candidate for a maximum. But here's the thing. What is f of 0? Yeah, that should be a confusing question because f of 0 does not exist. So we cannot have a maximum there. The function doesn't exist there. Hence, we have no relative extrema. Since we know from the extreme value test, the relative extrema can only occur at critical points and endpoints. We have no endpoints, and our critical point is an asymptote. So we do not have any relative extrema for this function. If you have any questions about that, please let me know. Now let's move on to the next part. Find where f is concave up and where f is concave down. Well, concavity, that means the second derivative is involved, right? And to find the second derivative, we first need the first derivative, which is negative 2 over x cubed, which is equal to negative 2x to the negative 3, right? So that's our first derivative. Now we need our second derivative. And f double prime of x is equal to 6x to the negative 4th, which is equal to 6 over x to the 4th. Now, to figure out where the concavity is, we need to first find where does it have no concavity? Where is it neither concave up nor concave down? Well, that's where the second derivative is equal to 0 or does not exist. Since the second derivative is never equal to 0, we can conclude that the only place it does not have concavity is at x is equal to 0. F double prime of x does not exist. Nosy and trend here. So now let's pull up our little chart. Plot x is equal to 0. Pull out our test values. Let's pull out negative 1 and 1 again. And we test our second derivative. So notice we put negative 1 into our second derivative. That's going to be positive. Plunge 1 into our second derivative. That's also going to be positive. What do you know? We have positive concavity everywhere except x is equal to 0. So for our answer, we can conclude that we are concave up on the interval negative infinity to 0, union 0 to infinity, and it's concave down, nowhere. And that is our answer. We found a second derivative, figured out where it did not exist, built our little chart, pulled out our test values, test the function in each interval, conclude that is where it's concave up or where it's concave down, and we have our answer. And now, for part E, find any inflection points. Now, to be an inflection point, the function must change concavity at that point, and it must exist. That point must exist in the domain of the function. So, we notice the only possible candidate is x is equal to 0. But at x is equal to 0, the concavity doesn't change, and the function doesn't exist at that point. So we really do not have any inflection points. So we conclude we have no inflection points. And our job is done. Once again, I'm going to leave it to you to practice graphing these. If you want to give the sketch a try and send it to me, I would be happy to look at it for you. So that's a couple of examples I have on graphing. If you go back and look at our slides from sections 4.3 and 4.4, you'll find even more examples on how to use the derivative and its information to sketch a graph accurately. Notice, almost all these applied problems we have done have one thing in common: the derivative and analyzing its behavior. The derivative gives us a lot of information, guys. It gives us a whole lot of information. So it's vital that we understand how to take derivatives and analyze them. All right, that's all I have for you on this review with the graphing, and I will see you all next time where we will have more fun with math.